result here that's actually related to, I think, Mersenne primes for the case k equals to 2. But we can just prove it in general for an arbitrary k. Now, just a little bit about what this vertical bar means. 3 divides 12 means the very same thing is 12 is congruent to 0 mod 3. Okay, the triple bars here for congruence, a lot like equality actually. 12 is congruent to 0 mod 3. So that's the connection. And also it's the same thing as saying 12 divided by 3 is an integer. In this case it would be 4, right? Won't write that down. Okay, now, so it's really a fairly straightforward proof. Right here we're trying to prove this, but I recast it using congruence notation in much the same way we did this, very same sort of idea. Okay, now again, fairly easy. This first step is quite obvious. A number is congruent to itself. It's like saying 6 is congruent to 0 mod 6, right? 6 minus 0 is divisible by 6. So this is trivial, but when you add 1 to the other side of this equality, and you can think of it like that, you get this statement, you know, that follows from the triviality. And from this statement, we can write down k. And this is the advantage of congruences. You can treat them in very much like equalities in so many cases. Okay, so we can raise both sides to the a power. Remember, a is odd, and so that's where we actually, this is the only time we're really, quote, doing anything in the proof. Okay, so this would be minus 1. Oops, that's an a right there. Raised to the a power. Okay, that's my a, folks. Sad state of affairs when that's an a. It's not an o. Okay, now raised to the a power. Now recall it was hypothesized or given's a better word, that a is odd. So up here a is odd. Okay, and we all know that a negative raised to an odd power is going to retain that negativity. And so what we get right here is, rewriting this, you can write this as k to the ab if you want to, just properties of exponents. So you can write this as k to the ab as a product, a product for your exponent, that is. Okay, is congruent to negative 1. All right, and again, I'm leaving this out, but that's mod. I should have written it on the previous step. That's mod k to the b plus 1. Okay, but of course you can rewrite this as k8. Just subtract or add 1 to both sides. You can get KAB, adding 1 to both sides, plus 1. Is congruent to 0. Okay, and of course I won't rewrite this, but this is k to the b plus 1 modulo k to the b plus 1. But remember, that's exactly what we were trying to show. Okay, that's exactly what we were trying to show, is that this statement, k to the b plus 1, the smaller one, divides the larger one, is equivalent to this congruence. And we've shown that this congruence holds up. And so we can write a QED right here if you want to. Thus we have demonstrated. Quandam est demonstrandum, maybe something like that. Okay, so that's the end of the proof, folks. And let's take a look at just a concrete example. And I'll let technology do this, but y'all, here's an example of where b would be equal to 6. Okay, and what do we have for a? A would be 5, right? B equals 6, a equals 5, so a equals 5, which is odd, right? A equals 5 is certainly odd. Okay, and check it out. This is just taking 53 to the 30th, of course, is nasty. I mean, huge. So, but anyway, we've shown that you do get an integer right here. Okay. Okay, when you divide that and that, you get an integer, which is consistent with the result we just established. Okay, everybody. I hope you enjoyed that. We proved what we set out to prove. Right there. Yep. Okay. Thanks for viewing.